All right, we're working on lesson 2.6, higher order derivatives. Two topics here we need to cover: how to find the higher order derivative and what some applications of that are going to be. And again, throughout this, if you need time to write down something that's already being presented, just hit the pause button. So what is a higher order derivative? Well, essentially it's taking a derivative of a derivative. It's a rate of change of a rate of change. So first of all, going into some notation. We've talked about the notation of a first derivative, y prime, f prime of x, or dy dx. That's the first derivative. Okay. If we're going to take a derivative of that, that becomes the second derivative. Y double prime or f double prime of x are the most common notations. If you're going to take a derivative of that, it becomes a third derivative, y triple prime or f triple prime of x. And then it continues. You can have a fourth derivative, a fifth derivative, and so on and so on. And it follows, finding a second derivative follows the same rules and guidelines as far as product rule, quotient rule, chain rule as a first derivative. So homework will start out with a pretty easy example, something like this. Find the first three derivatives of this function, meaning find the first derivative, find the second derivative, find the third derivative. So you start with the first derivative, and we just find the derivative of each individual term. So starting with the first term here, 6x squared, that's just an application of the simple power rule. Derivative there would be 12x. Move on to the next term. The derivative of 24x is 24, and the derivative of negative 8 is 0. So there's your first derivative. Second derivative would be the derivative of the first derivative. So now we need to take the derivative of that. And again, go term by term. The derivative of 12x is 12. And then the derivative of 24 is 0. And then the third derivative would be the derivative of the second derivative. The derivative of 12 is 0. So those are the first three derivatives of that function. And honestly, as far as what to see and expect in your homework, it doesn't get much more challenging than that as far as just finding a number of derivatives of a simple function. Now, moving into applications, one application we're going to look at, actually the only application at this point at least we're going to look at, is the acceleration of a falling object. So we talked in lesson 2.3 about the position function s of t. If we took the derivative of position, that gave us instantaneous velocity, which was v of t. That's the rate of change of position, okay, in feet per second normally. If we took the derivative of velocity, so that's the rate of change of velocity. For example, if you're on the freeway going 60 miles per hour consistently, then your velocity isn't changing. You don't have a rate of change of velocity. But if you're on the freeway and you're getting faster, going from 50 miles an hour to 60 miles an hour to 70 miles an hour, then your velocity is changing. The only way for velocity to be changing is if you have acceleration. So if you took the derivative of velocity, that would be the second derivative of position. You'd end up with acceleration. So acceleration is the double or second derivative of position. It's the first derivative of velocity, and acceleration represents the rate of change of velocity in feet per second squared. So an application we need to look at. Again, much like the problems from section 2.3, a ball is thrown upward from the top of an 80-foot cliff with initial velocity of 64 feet per second. Position functions given here, where t is measured in seconds. Find the height, the velocity, and the acceleration of the ball at time t equals 2. So what they're asking us to find is find s of 2, that's the position, or height. They want to find v of 2, that's the velocity at 2 seconds, and they want us to find acceleration at 2 seconds. position of the ball after 2 seconds, we can just use the position function. So S of 2, plug 2 in for time into the position function. So negative 16 times 4 is negative 64. 64 times 2 is 128. Now, adding this all together, let me get my calculator out. Got negative 64 plus 128 plus 80. That's equal to 144. So what this is saying is the ball was thrown upward, started at 80 feet, so after 2 seconds the ball has gone up as high as 144 feet. At this point I'm not sure if it's still traveling upward or traveling downward, but we know the height is 144 feet. Now, we need to find the velocity at 2 seconds, so velocity is equal to the derivative of position, so it's going to be the derivative of our position function. Here, if we took the derivative of that function, we're going to get negative 32t plus 64. So now the velocity at 2 seconds is negative 32 times 2 plus 64. So velocity is 0 at 2 seconds. How do you reconcile that? What does that mean? Because if the ball's thrown upward, it's either moving up or down, so then how could it have a velocity of 0? So hold on, 0 feet per second. There we go, need to be precise. What this means is the ball has reached the top of its trajectory and is going to start to fall at that moment. So when does the ball reach its maximum height and start to fall? It's at 2 seconds according to this. That's where the velocity is 0. Now lastly, we need acceleration. That's the derivative of velocity. So that's just going to be negative 32. There's no variable, so there's nothing to plug in here. The velocity is just negative 32 feet per second squared, and that's just the effect of gravity on the surface of the Earth. Is all that is. So that's going to be the same regardless of the initial velocity, regardless of the initial height. The acceleration of a falling object is constant, and if it's in feet and seconds, it's negative 32 feet per second squared. And that's about as much as you need to know at this point about an application of the second or third derivative. And that would be the end of lesson 2.6.